My name is Stephen Kwesi, and in this video I'll walk you through a digital logic circuit known as a one-bit arithmetic logic unit, or ALU for short. Now, this simple but powerful circuit performs basic arithmetic and logic operations on binary values using only logic gates. Over here, you can see that the circuit takes three binary inputs. We have the first input A, the second input B, and then the carry-in input, which supports more advanced operations like full binary additions. Now, the goal of the circuit is to process these inputs and produce two outputs. That's the sum and then the carry out output. Now, in this circuit, there are some core parts, and one of the core parts is the full adder logic, or the full adder circuit, which is over here. Now, the core of this circuit is a full adder, yes, already mentioned. It's built from logic gates, basically. This is how it works. So, first of all, I used an XOR gate to compute A XOR B, or A exclusive or B. So, that is what we have over here, A and then B. And I decided to name this X1, right? Then we take the results and the XOR, sorry, we take the results and XOR it with the carry in, right? And the goal is for us to get the sum. Now, over here, we have the multiplexer, but for now, let's neglect the multiplexer and assume that this computation that is happening over here is what is giving us the sum, right? So, you can see the carry in connected here, then the A exclusive or B, the result is also connected here, right? Now, um, for the carry in logic, two end gates, two end gates are used, and I named them C1 and C2. So for the C1, it takes A and B, and for the C2, it takes X1 and then the carry in, right? Then at the end, there's an OR gate which combines the two end gates. So at the end of the day, we have C1 or C2, which is going to give us our carry out results. Now, this setup allows the circuit to add three binary inputs and give a correct result. Okay, so earlier on I mentioned that we should neglect the multiplexer, but then now our focus is on the multiplexer. Over here we can see that we are not using an actual multiplexer, but then we have replaced it with logic gates that manually um, work as a normal or default or built-in multiplexer would, right? So like I said, the circuit manually implements the multiplexer's behavior using logic gates, and in the previous video I did more explanation on what the multiplexer does and what it's all about. Now over here it's a 4 by 1 multiplexer, right? It has a NOT gate to invert the control signals and AND gate to mask the inputs based on the signal, and an OR gate to combine the chosen results. Alright, so moving on to the output. After processing, the circuit produces two outputs, which I already mentioned, the sum and then the carry out. The sum is the actual result of the bitwise operation, and then the carry out is a signal that tells us whether the result carried over or not. I'm going to do some illustrations, but before that, I would like to talk about what a one bit ALU actually is. So it is a small digital circuit that performs arithmetic logic operations, and it does that on a single pair of bits. It focuses on addition, but with simple modification. They can be extended to include logical and even subtractions. Now, the multiple one-bit ALUs can be connected together to build larger processes capable of handling multi-bit operations. In summary, this one-bit ALU circuit uses only logic gates, no dedicated multiplexer. Everything is basic logic to perform arithmetic operations and control output logic. It is um, a compact and educational example of how complex digital behavior is built from simple components like AND or XOR and NOT gate. Alright, so now I'm going to display um, yes, so this is a truth table I have over here, and then I'm going to simulate the values here and see whether we'll get the sum and then the carry out values. If we get them, then it means the circuit is rightly connected. Okay, so for our first input, we have 0 0 0 0 0, right? So basically, the three inputs A, B, and carry in are all zero, and they're saying that the sum is also zero, and then the carry out is also zero. So yes, we can see over here that our sum was zero, and then our carry out is also zero. Now, if you look at A being zero, B also being zero, and then the carry in being one, the carry in being one. When I change carry in to be one, you can see in the table that our sum becomes one, and then our carry out becomes zero. So I have to turn on the selectors of the multiplexers. So you can see that our sum has become one, and then our carry out is still zero, right? It's basically adding in base 2. So 0 plus 1 will give us 1 at the end of the day, right? And when we look at 0 1 0, 0 1 0, 0 1 0, we get our sum to be 1, then our carry out 0. So 0 1 0, our sum is 1, carry out is 0. Alright, let's move on to um yes, 1 0 1, 1 0 1, 1 0 1. Now 1 0 1, over here our sum will be 0, and then our carry out will be 1. So so yeah, 1 0 1, 1 0 1. You see that from here 1 0 1, our sum becomes 0, and then our carry out becomes 1, right? Now what it means is that when we sum 1 plus 0 plus 1 in binary, we end up getting 0 remainder 1. The remainder 1 is what is illustrated by the carry out, and then the 0 is the sum, because we can't get 2 in base 2, right? So that is how the one bit ALU or arithmetic logic unit works, right? It performs arithmetic operations and then logical operations. Alright, thank you very much.